Hello everyone, let's discuss the numericals on Van't Hoff factor. Let's see that. 0.6 ml of glacial acetic acid with density 1.06 gram ml inverse is dissolved in 1 kg of water and the solution froze at minus 0.0205 degrees Celsius. Calculate Van't Hoff factor and Kf for water if its Kf value is 1.86 Kelvin kg mole inverse. So let's begin with the given. The solvent is water and the solute is acetic acid. Its molar mass is 60 gram mole inverse. The data says that 0.6 ml of acetic acid, that is nothing but V2, which is 0.6 ml, and its density is given, that is ρ2, as 1.06 gram ml inverse. Dissolved in 1 kg of water, it means that W1 is 1 kg and the solution is going to freeze at 0.0205, that is nothing but TF observed, which is minus 0.0205 degrees Celsius, and the value of Kf is 1.86 Kelvin kg mole inverse. What we need to calculate over here is Van't Hoff factor, that is nothing but I, and the formula which you're going to use over here is I is equals to delta TF observed upon delta TF theoretical. Having this data, let's go ahead with the entire calculation. The calculation says that for solution specifically, if I talk about this, we need to first find delta TF observed and delta TF theoretical. So let us first calculate delta TF observed, given by the formula T naught observed minus TF, that is T naught F minus TF observed, that is 0, minus of minus 0.0205, that is as good as writing positive 0.0205 degrees Celsius, that is nothing but 0.0205 Kelvin, because the difference of temperature in degrees Celsius and Kelvin remains the same. Once we are done with delta TF observed, now we need to find delta TF theoretical, which is given by the formula Kf into small m. We don't have small m, let's calculate that. It's small m is equals to W2 upon mW2 into W1. But in the question W2 is missing, but in place of W2 they have given its density and volume. So what do? In place of W2 we are writing ρ2 into V2. The denominator still remains the same. Substituting values, we get 1.06 into 0.6 upon 60 into 1, and this will give me the answer as 0.0106. That's the answer of molality. Once we get the answer of molality as 0.0106 and delta TF observed, let's now calculate delta TF theoretical, which is nothing but Kf into small m, which is Kf 1.86 into 0.0106, which will give me finally 0.01972 Kelvin. Now once I know what is delta TF theoretical, let's calculate the value of I, given by the formula delta TF observed upon delta TF theoretical. Delta TF observed, we know it's 0.0205 and theoretical is 0.01972, which on further solve will give me answer as 1.03952 as the value of I, that is Van't Hoff factor. Let's take some multiple choice question. The first one, which of the following pair of solutions are isotonic? So there are 4 options and 4 pair of solution given to us. Now the condition is that for a solution to be isotonic, their concentration has to be same. So if I take option A, which is 1 molar urea and 1 molar KCl, you might wonder that both of them have the same concentration, but they are not isotonic. Because whenever you have an electrolyte as a solute, you have to consider the Van't Hoff factor. Now, for urea, the Van't Hoff factor is 1, but for KCl, the Van't Hoff factor is 2, because it will dissociate as K plus and Cl minus. So you have to multiply that initial concentration by 2. So what do we get? In reality, you get something like 1 molar urea and 2 molar KCl. Now if you look at option B, it is 1 molar urea. Urea is a non-electrolyte. The Van't Hoff factor is 1. So its actual concentration remains also 1. Glucose is also non-electrolyte. So the concentration is still 0.01. So here also the concentrations are not same. If you check option C, it's 1 molar KCl. KCl having the Van't Hoff factor 2. And 1 molar BaCl2. BaCl2 having the Van't Hoff factor 3. So if you multiply, you will get something like 2 molar KCl and 3 molar BaCl2. So even here in this case, the concentration are not same. If I go with option D, it's 1 molar urea and 1 molar sucrose. It will remain same because it is a non-electrolyte. If I look at all these 4 options A, B, C, D, then I can say that my correct answer is option B, where the concentrations are same. Let's check one more MCQ. Which of the following solution will exhibit highest osmotic pressure? Now for exhibiting highest osmotic pressure, the concentration has to be highest. Now we have to check in which case the concentration is highest. When I say 1 molar urea solution, its actual concentration is also 1 molar only, because urea is a non-electrolyte. For glucose solution also it's 1 molar because it is a non-electrolyte. But for alum, it is not 1 molar, it has to be 8 molar. The reason is alum's formula is K2SO4 Al2SO4 thrice 24H2O. And this alum will dissociate as 2 of potassium ions, 1 of sulfate from K2SO4, 2 of aluminium from Al2SO4 and 3 of SO4 from Al2SO4 thrice. On addition it gives me 8, so it is 8 molar. And if I talk about NaCl solution, it will give me 1 plus 1, that is 2, so it is 2 molar. So from this I can say that my answer is 1 molar alum solution will have the highest osmotic pressure because its concentration is highest. Let's take the last multiple choice question. Which of the solution will exhibit highest boiling point? 1 molar KCl, 1 molar urea, 1 molar NaCl, or all of the above. For exhibiting highest boiling point, the concentration once again has to be highest. So if I talk about 1 molar KCl, it's actually 2 molar because its Van't Hoff factor is 2. Urea will still be 1 molar, but NaCl will now become 2 molar, and D will be not the appropriate option this time. Now here I am confused between option A and option C. So what has to be done? In that case, you have to select for highest boiling point the one which has a low molar mass. So KCl has the molar mass 74.5, NaCl has 58.5. So I'll go for option C, having the lowest molar mass. That's all we have for this particular module. Thank you so much.